Recording is rolling. It is Thursday, October 31st. Got two more puzzles to go on this page. So chapter 7, we did a bunch of these yesterday. We got a question about asteroids and a question about a cannonball on the moon. We're going to knock those out. Then you guys have your laptops up ready to go because later in class, we're going to do a Kahoot on satellites. Tomorrow is going to be turntable of friction lab. I'll break out those turntables and have you guys figure out what is the coefficient of static friction between, say, like one of these masses and the turntable surface. I look something like this. Okay. Then, before you guys walk out of class today, I have you guys' next take-home quiz right here. Guys, when is that take-home quiz going to be due? Monday. And the puzzles we're about to finish right now, when are those due? Friday. Yeah, tomorrow, which if you want to turn them on today, you probably could, because you're finishing them, right? Oh, speaking of Friday, guys, when do you get out of school tomorrow? Yeah, 3:30. You guys know tomorrow's a full day? All right. Let's with all that, take a look at chapter 7 questions. We did these 3 yesterday. We're on number 72 asteroid. Okay, sorry, 72 asteroid. The asteroid series has a mass 7.0 times 10 to the 20 kilograms. Let's write this down. 72. Mass of series is 7 point, well, you say 7 here, okay, times 10 to the 20 kilograms, and a radius of 500 kilometers. Okay. Because I forget the question being asked, but let's just look at these numbers for a moment. I mean, they're going to ask something where probably think we need some equations and do a calculator and don't. Okay. When you're doing your calculations, do you want to plug in the number 500 for the radius? No. No, you want to plug in eventually what? 500,000. That's right. Yeah, 500,000, because that's how many meters it is. Okay. If you have base SI units, mass could be in kilograms, but the radius could be in meters. Right. So what are they actually asking though? 2 questions. What is the gravity field on the surface of Ceres? And follow-up question, part B, how much would a 90-kilogram astronaut weigh on the surface? Right. Ceres, by the way, is I think it's the largest asteroid in the asteroid belt. It's a big one. They used to consider it a planet. Like if you were in school, like in 1910, I think you would have learned the planets of the solar system, and this would have been one of them, right? But no, it's just a big asteroid that kind of hard to see from Earth anyway. Okay. All right, so gravity field. Do you guys know a formula for gravity field? That expression, it's a fraction. It goes what over what? GM on R squared. Oh yeah, GM on R squared. Right. So universal gravity constant, the mass of, well, in this case, the asteroid, right? The radial size squared. Really? Oh, I guess I have to give you G. You guys remember G is 6.67 times 10 to the negative 11. That's Newton meters squared per kilogram squared. Right. Oh, there's base SI units, right? Meters, kilograms, all do. Right? Let's just put it all together. Can you guys just put this together? So I got G, 6.67 times 10 to the negative 11. Meters squared per kilogram squared. We got the mass of Ceres, which is 7 times 10 to the 20 kilograms. All right, guys, if you wrote this number out in an expanded form, it would go 7 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 kilograms. And then that's by a scientific notation. It's easier. And then divided by the radius squared. Guys, can I say 500 squared?
No.
Aha, you caught me. 500,000 meters. And square that. Aha, got it. All right. So last part. Can you correctly plug that into the calculator? Okay, I'll do it. You guys do it. Let's see if we get the same thing. All right. Can you correctly put the parentheses where they have to go? And the scientific notation, can you type that? Will do. All right. So I have this all typed in. I have not hit enter yet. I want to make sure you guys are caught up. I want you guys to get it first. Okay. All right, so you guys getting the gravity field on this asteroid? Okay, got some paper here if you need some paper. This guy's got paper, looks like. You guys know I'm going to take up these puzzles. They're due tomorrow, right? Yes, sir. Doing with you guys. Yeah. All right. What are you guys getting for the gravity field on this asteroid?
I got it.
I got, like, 4.
9.
I'm getting. Oh, I heard somebody say 0.18.
Oh, that's nice.
Yeah. Right. 0.186 something. Yeah, I'll round that a little bit. Right. Oh, and guys, this number has units. What's the units? How to measure gravity field? Meters per second squared. Exactly. Right. I say, or you might see this sometimes, Newton per kilogram. It's the same thing. But yeah, there you go. 0.19 meters per second squared. And that looks believable because what is the gravity field of Earth? Yeah, about 10 meters per second squared. Right. So yeah, whenever you get an answer in physics, say, what can I compare that to? What is that? Right. Yeah, I think it looks about right. No, I want to do my own extension question here because I've been wondering, if you were on the surface of this asteroid, what if you jumped really hard and you jumped really high? Could you just straight up jump off the asteroid? That was the question I was wondering. Guys, jump off the asteroid. Does that sound like a question for escape speed? You think? Let's do this one real fast. I got a bonus question. Here, I won't even write down. I'm just gonna plug the numbers into this expression. Could you jump off Ceres? Square root. How fast would you have to jump for that to be the case? I got a 2. I got a 6.67 times 10 to the negative 11. I got the mass of Ceres is 7 times 10 to the 20. And then divide by, and then 500,000 meters, right? All right, let's see, how fast do you have to jump to accidentally jump off the surface? It would be, ooh, do you guys see that number right there? You guys tell me, is that something feasible? Do you think you could jump off the surface of this asteroid? No, because guys, 432 meters per second. That's like hundreds of miles per hour. Yeah, nobody can jump that fast. So that. All right. A little side thought. All right. So there is a follow-up question. It says, what would an astronaut weigh? So 72B. That was 72A right here. We're doing 72B. A 90-kilogram astronaut. Guys, weight. Actually, you have two perspectives on weight. You could go G-M-M over R squared, or you could just call it mg. If that goes to the same thing. You guys remember? We did this yesterday. So you guys remember this from yesterday. You guys see this part that is just circled in gold ink right there? You guys see the GM on R squared I just circled? That is equal to what? Yeah, gravity field. That's that little G right there. Right. I think had you guys calculate that in your notes few days back too. Right. So just pick your favorite one. Here, I'll just do this one right here. Let's do 90 kilograms astronaut and a gravity field of 0.19 meters per second squared. Come out to. All right. I'm looking at 17.1. What's the unit? 17 what?
Meters per newtons.
Newtons. That's a weight. 17 newtons. Okay. Ooh, guys, how much does your largest lab mass weigh?
Is 500 newtons, right? Or 500 grams?
But
Something.
so it's 1 kilogram mass, which weighs how many newtons on Earth?
1.
Like 10 newtons, right?
10.
Right. Because guys, 1 kilogram times 9.8 meters per second squared. That's like 9.8 newtons, right? Right. It takes 9.8 newtons of force to pick this up. Right. All right. Hey, that's kind of close to this number. So if you're an astronaut bouncing around on Ceres, boing, 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 maybe you'll probably weigh about this much. All right. There you go. Are you guys ready for the last one, number 92? Then we'll be finished with these puzzles, and I bet some of you guys might even want to turn these in a few minutes. Get them off your hands. Number 92, cannonball. The moon's mass is 7.3 times 10 to 22 kilograms. Let's get this on the board. Mass of the moon, they said is 7.3 times 10 to the 22. That's kilograms. Okay. Oh, pause right here. I've got my own side question again. I always have my own side questions, right? Right. I might throw on the mass of the Earth, which I know because I've been using this number so much. 5.9 something times 10 to the 24 kilograms. You guys used that number yesterday a few times, right? You guys remember mass there? Okay. I want to do a comparison. So first of all, let's look at this number, compare this number. Guys, 6 compared to 7. Isn't that almost the same number? 6 and 7? Right. So I want to know how massive is the Earth compared to the moon, which since 6 and 7 are almost the same number, that's really an order of magnitude question. So You guys see 10 to the 24 versus 10 to the 22? You guys see that? All right, question for you guys. How massive is the Earth compared to the moon? The Earth is
100 times.
100 times. Yeah, 100 times because it's 10 to the power of 2. Ah, you see 100 times? All right. What else do we know? They told you the radius of the moon. Radius of the moon. They said it's 1,785 kilometers. Okay. Now, I bet we're going to have to do an equation here because it's physics class. When you plug in the radius of the moon in your calculator, do you want to type in 1,785?
No.
Oh, what would you type? That's right. Tag on 3 zeros. Because that would be in meters. Oh, yeah. That's right. So what's the question, though? If Newton's thought experiment of firing a cannonball from a high mountain attempted on the moon, how fast would the cannonball have to be fired, say, to go in a circular orbit? And how long would it take for the cannonball to return back to the cannon? Draw a picture for you guys. So here could be the moon. Say on the moon, there's a tall mountain right there. Okay. Now I don't think to scale there's a mountain really that tall, but just get the idea, right? And we're going to put a cannon on top of this mountain and fire a cannonball horizontally. Right? So there's some speed here called V. It's got, right? Let's say it just goes into orbit around the moon. Right? Fired it just fast enough, and eventually gets back to the cannon. Right? So here's the radius of orbit, which is basically the radius of the moon. So I'll just call it the same thing. Okay, got that. All right. Well, they asked how fast? How fast would you have to fire that? Hey, guys, how fast to go in orbit? That's called what kind of speed? That's right, orbital speed. Yeah, orbital speed. All right, let's show you guys the top part of that poster. Do a little challenge right here. Challenge review. Can you derive the expression for orbital speed from scratch? Got a challenge question for you guys. Go ahead, write on your paper. See if you guys can do the derivation from scratch. Because that's something I want you to get out of this class is, can you relate equations to each other and do some algebra and solve for things?
Yeah.
We're going to find out. Can you derive orbital speed? You're going to see, here, I'll give you guys some hints. You're going to see the mass of what's being orbited. You're going to see universal gravity constant, that capital G. Maybe the mass of the cannonball in this case might show up in the equation, but probably cancels out.
Isn't it the square root of GM over R?
Yeah, that's the answer. That's the answer. Right. Now, do you remember how to get to the answer? Ooh. Right. Yeah, it is root GM on R. That is correct. Right. So, guys, remember anything in orbit. Here again, this is what I want you guys to get out of this class is how to think about things. Is that whatever's in orbit, there's only one force on it, which is the gravity force. And that gravity force is acting as a centripetal force to hold it in a circular path. Right? Guys, do you guys know an expression for, let's start with centripetal force. What's an expression you guys know for centripetal force straight from your lab? Boom, mv squared on r, exactly. And what's let's do the universal form of gravity force. It's a big fraction. It looks like what?
G, mass 1, mass 2, over R squared.
Aha, GMM on r squared. Guys remember that? Right, right. And if that is that, then can you solve for that v for orbital speed, like a tangential velocity of speed? Right? Because what variable cancels out? Yeah, the low mass. In this case, the mass of the cannonball, right? And then you get exactly what Ethan said right there. Screw GM on R. Right? Boom, just like that. All right, so let's just go ahead and apply that. Let's say orbital speed, we'll just jump straight to the expression, is root GM on R. Okay, right. Plug some numbers in. Big old fraction right here. 6.6. All right, you guys are writing this as I'm writing it. 6.67 times 10 to the negative 11. That's meters squared per kilogram squared. We got a mass of the moon. Maybe I should call this capital M because it's what's being orbited. Right, the moon has some mass capital M. The cannonball is little m. That's what it should be. So this is 7.3 times 10 to the 22. And that's kilograms. That's the mass of the moon right there. Okay. Then divide by the radius of orbit. I'll just call it the radius of the moon. That's that many meters. Right. Finally, make sure that when you plug this into your calculator, you have everything grouped correctly. That's part of the fun of this chapter is can you navigate scientific notation and parentheses, square roots and fractions. Right, there's a lot going on here. So I'll do it, you guys do it, and let's see if I'll get the correct orbital speed. Right. Give you guys a little hint is remember if you have this model calculator, which you do, then we open up a square root. This calculator gives you one parenthesis. I'm going to open up excess parentheses because as soon as I close it, it stops rooting. But I want to root this entire expression. So I have excess parentheses to make sure I don't accidentally close it too early. All right, I got mine plugged in, and then this model calculator automatically closes the excess parentheses. Not all calculators do. Right, so I got that typed in. You guys got it typed in. You're getting there. I want you guys to get it first. So give you guys a got there. Right now, when I hit it, oh yeah, which guy?
I got 1651.6. Yes, I did.
Huh?
I got 1651.6.
All right, I think Ethan, Aiden, and Carson all got about 1600 something.
Yeah.
All right, I think that sounds about right. And here's why. Does anybody remember what is the orbital speed around the Earth? What's the past tense of eat, gang? 8 kilometers per second. Should I guess that Kahoot video? 8 kilometers per second, which is like 8,000 meters per second. You guys think you don't have to maybe go as fast to orbit the moon?
Yeah.
Yeah. So see if I'm getting what they got over there. Good. Oh yeah, look at that. 1,652 some and what unit is that? Meters per second. That's right. Right. That's how fast you have to go orbiting the moon. I bet if you went back to the 1960s, all the NASA scientists and engineers are like looking at this number saying, well, that's how fast we got to go to be orbiting the moon as part of this Apollo mission. All right, next question. How much time would it take for the cannonball to make one complete trip around? Now, time to go around. Here, this is something similar to what you guys saw yesterday. So let me walk you guys through this thought process. Is if you know how fast it's going around, which we just found, and you know the distance around, guys, what's the distance around a circle called? Circumference, right? Can you, if you know distance, you know speed, can you solve for time?
Yeah.
Right? Right. This speed right here is distance divided by time, isn't it? And the distance around is one circumference. Guys, what is one circumference in terms of this radius?
360 degrees.
2 pi r. Yeah. So I would put a fraction here. In place of v, I would write 2 pi r divided by t. And we're solving for t. You guys get that? Right? Now, we did that yesterday. And in class, I showed you guys you could solve for t, and you could effectively derive Newton's version of Kepler's third law. We did that yesterday. It's already in your notes. Right, so let's just pick up from that point. You guys did already. So I'll just straight to, this is part B. That was part A over here. Right, so 92B, we got the time to go around is, so for a circular orbit, it ends up being 2 pi times the square root of, and then the distance cube, well, radial distance cube divided by gm. So maybe something like that. Okay. Which mass does this refer to? The mass of the moon. Yeah. If you're orbiting the moon. Right. So this is a cannonball orbiting the moon. Does the mass of the cannonball show up anywhere in that equation? Nope. All right. So you guys plug it in. I'm gonna write the numbers in here. John, why don't you guys get the answer before I get the answer? So All right. Try this out. All right. I got mine plugged in. You guys got plugged in? Let's do one more thing. I think I got enough paper over here. Because when you hit enter, you're going to get a number. That's going to be some number of what? What's the unit? Seconds. It would be in seconds, wouldn't it? No, do you guys think it's a crazy number of seconds to orbit the moon? What would be a more reasonable unit, do you guys think? Hours? All right. How do you convert from seconds to hours? I'm going to squeeze it in right here.
Divide by 60.
Times by 360.
Oh, divide by 60.
Divide by 360.
To convert the hours?
Yeah.
Oh, how about this?
Seconds.
I threw in some railroad tracks right there. Now, there's some crazy large number of seconds. I want a smaller number of hours. Let's go 3 minutes. How many seconds in a minute?
26.
Does the number 60 for seconds to minutes? Let's do seconds to minutes. Does the number 60 go on top or on bottom? Down here. There's 60 seconds in 1 minute. All right, so all these crazy units in the square root consolidate to seconds. It's going to cancel out with the seconds. Okay. And then minutes to hours, same thing. 60 minutes, 1 hour. Minutes goes away. All right, it's going to leave you with hours. Right. Or if you want to do this all in one step instead of two, guys, how many seconds are in 1 hour? 3,600. Oh yeah, because 60 times 60 is 3,600. Okay. All right. So I'm gonna hit enter and then divide by 3,600. All right. And I'm getting a time period of 1.89 hours. All right. Are you guys getting that too? Guys getting that? All right. I'll tell you what. This surprised me. Last class, I got the same number, and I had to do a Google check, and Google said, "Oh yeah, it takes about 2 hours to orbit the moon." Here's why this surprised me, because how long does it take to orbit the Earth in low Earth orbit? 90 minutes, right? So I was thinking, well, the moon is physically smaller, and the Earth is physically larger. I know it'd probably take a long time to orbit Jupiter, I think. So I was expecting this number to be less than 1.5 hours, right? But anyway, I think that's actually correct though. All right, so you guys good? You guys good? All right, guys ready for a Kahoot?
Yes, sir.
Kahoot
I don't
time.
know about it.
All right, we're back and ready to go. The pin is on the board, not quite in yet. All right, and these are questions on satellites and satellite motion. Oh, there it is, satellite motion.
How can any mathematical problems I can answer them in gym.
Satellites. The orbital speed for a satellite in low Earth orbit is?
No, that was a trick.
Yeah, what's the past tense of eating? 8 kilometers per second. There you go. Orbital speed, Earth numbers. There you go. All right. Points on the board. Amina, Alec, Carson, Evan, Nathan. The speed of a satellite in circular orbit, if it's a circle, would be a constant speed. Right? We're not going to say constant velocity because the direction is changing, but yeah, constant speed for a circular orbit. Amina, Alec, Carson, Evan McNugget, Nathan. The speed of a satellite in elliptical orbit. Elliptical. Yeah, that's right. It's going to be speeding up and slow down a little bit. You know what that kind of reminds me of is I bring us over here. Where's Kepler? Do I have Kepler here? Here's Kepler. You guys remember this? So if it's far away, it's going a little slower. If it's closer, going a little faster. You guys remember equal areas and equal times? Kind of remind me of that. All right. Down. All right, I got Amina, Alec, Evan, Carson, Nathan. The time period of a satellite is defined as Yeah, the time to orbit once. Yeah, so the time to make one complete revolution. All right, Amina, Alec, Carson, Evan McNugget, Nathan. The higher the satellite is, the yeah, the less its speed is, right? So a couple of perspectives on that. Oh, what's going on? All right. I bet you could navigate this. The well, actually, here's a better one: is orbital speed. How about this? Orbital speed right here. Okay. So, guys, the higher in elevation it is, isn't this R increasing? If this R increases, does this V decrease? Think of it that way, right? Or you could do Kepler's laws. There's a connection there too. All right. Ooh, Victoria Molly on the board. Evan, Amina, Nathan, Carson. A circle is a special case of
Hashtag ellipse.
yeah, ellipse. You guys remember making an ellipse the other day with the string? And so you guys put down two pens as focal points and drew the ellipse. If those points were on top of each other, that would be a circle. Yeah, so a circle is a special kind of ellipse. All right, Victoria Molly, Alec, Amina, Nathan, Carson. The circular orbit of a satellite orbiting Earth is characterized by a constant. So, circular orbit has a constant. Yeah, all the above, all those. All right, constant speed or tangential velocity, constant. Guys, what type of acceleration are we talking about? A centripetal, or you could have said gravity field too, because it's the same thing. And yeah, and constant radius for a circle. Yeah, all the above. All right. Evan, Amina, Victoria Molly, Nathan, Carson. The fastest moving planet in the solar system is fastest moving. Closest to the sun. Right? Close to the sun. It's moving faster. Right. All right. So faster orbital speed. Oh, here I can back that up with an equation. It's right here. Boom. So universal gravity constant. This m can be the mass of the sun. This r is how far away you are from the sun, like center to center distance. Yeah. So if that's really small for say the planet Mercury, it's going to blow up to a huge orbital speed. Hey, just like that. There you go. All right. You got Big Willie, Mackenzie, Victoria Molly, Nathan, Carson. Pluto takes a longer time to travel around the sun than Earth because Pluto yeah, both of those together. It is going slower, right? It's so far out, has a slow orbital speed, but also it has a huge circumference around its orbit, a huge 2 pi r. Right? So for both those reasons, has further to go, it's going slower. Right? I checked on Google earlier. I think it was it 248 years? I think it takes Pluto to go around. It's more than 200 years for Pluto to go around. Big Willie, Mackenzie, Victoria Molly, Nathan, Carson, on fire. An object is placed exactly halfway between the Earth and the Moon. That object will fall toward. Yeah, it would be the Earth because the Earth is more massive. Now, guys, is there some point between the Earth and the Moon where the gravity cancels out and it would be in equilibrium?
Yeah.
Yeah, but that would be closer to the what? Closer to the Moon. Yeah, maybe call it the L1 point, like Lagrange. Okay. But yeah, if it's the geometric midpoint, it's gonna fall towards the Earth. The Earth is more massive, has more gravity pull. Mackenzie, Alec, Victoria Molly, Nathan, Carson. Projectile fired vertically from the surface of the Earth at, say, 10 kilometers per second. Take a guess. What's going to happen?
It might, it, ooh, um, um,
Yeah, rise and fall back down. Now, Chris, get back this up. So there's different speeds going on. You guys know orbital speed. If you run the numbers for Earth, this ends up being 8,000 meters per second about. Right? Oh, let me show you guys a different speed that we haven't covered this material yet in this class. I need to teach you guys conservation of energy first, but you can show that to escape the gravity field of a planet, you have to go this fast. Square root 2 gm/r. Right, so I'll show you guys that in the future. Right? Now, this is called escape speed. This is how fast you have to get a rocket to go so that you could cut off the engines of the rocket. And it's just coasting from inertia. And it still escapes the gravity as long as it's going this fast. Now, if you look at these two side by side, they look really similar. Here's orbital speed. Here's escape speed. You see escape speed? It's just going to be the square root of 2 times orbital speed. Square root of 2 is like 1.414. So since you guys know orbital speed around the Earth, let's try this out. All right, let's take orbital speed, which comes out to, actually, I think you guys got 7,907 meters per second when you guys put that in yours the other day. All right. And then I'm going to multiply by the square root of 2. It's like 1.414. Right. And here's the escape speed from the Earth, 11,180 something meters per second. So let's call it 11.8 kilometers per second. You guys got that? 11.8 kilometers per second. If you got a rocket going straight away from the Earth at 11.8 kilometers per second, it'll just barely be able to escape. Now, your guys' Kahoot question said 10,000 meters per second, 10 kilometers per second. So it's not quite fast enough. That's why it's got to fall back down. All right. Got Amina, Victoria, Molly, Alec, Nathan, Carson. A vertically oriented rocket that maintains a continuous upward velocity of 2 kilometers per second. A continuous upward velocity of 2 kilometers per second.
Oh.
Oh, what? Oh, where? Oh, where?
Okay. Now, guys, I just told you escape speed was 11 kilometers per second. Is that what I just said? Right? Guys, this is way less than that. Why can it still escape? And the key is that, continuous velocity. If you still have the engines on, you can still escape the gravity of the planet as long as you have the engines on. Because think about it this way. What if there was like a rope ladder from Earth to Mars? Do you think you could climb the rope ladder one rung at a time, like, and still get away from the gravity field of the Earth? Yeah, just very slowly. You don't actually have to reach escape speed to escape the gravity of a planet, as long as you have some continuous force applied. Okay. All right. Got Big Willie, Alec, Victoria, Molly, Carson, Nathan. The early bird communication satellite hovers over the same point on Earth indefinitely because
Orbital period is 24 hours, I would assume. The green.
yeah, they go orbital period of 24 hours. All right, so I want to get a picture going for you guys here. Here, I'm going to put a picture from last class. We got this question. I was trying to draw this to scale. So here could be the Earth, E for the Earth. You guys see this dashed path right here? This could be low Earth orbit, and that really is to scale. So there's the International Space Station on that dash orbit, right? Okay. But geosynchronous, oh, and that's what we're talking about, right? Geosynchronous. Here could be the early bird communication satellite. Takes 24 hours to go around. And I know where to put it because your textbook told you yesterday. It says it's at 4.23 times 10 to the 7 meters orbital radius. Now, if I divide by the radius of the Earth, 6.38 times 10 to the 6 meters, I can get a ratio. That ratio is 6.63 to 1. So you would need 6.63 Earth radii out. So this is 1 Earth radius right here. Here's 1 Earth radius. If I have about 6 or 7 of those, that'll get me out to early bird communication satellite. All right, there you go. And then the moon is even further away than that. Got Mackenzie, Big Willie, Victoria, Molly, Carson, Nathan. How long does it take a satellite in low Earth orbit to make 1 revolution around the Earth?
Oh my goodness. About 90 minutes.
Yeah.
90 minutes. There you go. Takes about 90 minutes. Okay. Are you doing those equations? All right. Mackenzie, Big Willie, Carson, Victoria Molly, Nathan. How long would it take a satellite located as far away as the moon to orbit the Earth? It takes way out there by the moon. Going around. How long that gonna take? Well, how long does it take the moon to go around the Earth? 28 days, right? Guys, moon, month. Guess so moon and month come from the same root word, right? Moon, month. Takes the moon 1 month to go around. 28 days. All right. If there's a satellite out there that has a different mass, the mass of the satellite doesn't matter. Right? Same time. All right. Got Mackenzie, Big Willie, Carson, Victoria Molly, Nathan. Compared to a satellite in orbit close to Earth, the period of a satellite far from Earth. So if you go from International Space Station to geosynchronous, like early bird, to like the moon, it could be in that order. Yeah, it takes more and more time. Okay, more and more time. Because they're going slower and they have further to go to orbit, like larger circumference. All right. Where does a satellite in elliptical orbit have greatest kinetic energy? Okay, we haven't talked about energy yet. Kinetic energy is energy in motion. So interpret this as where's it moving the fastest? Because where's the satellite moving the fastest?
Oh. At the point closest to the planet. Because the closer something is, the faster it is, speedier it is. The greatest kinetic energy will be going.
Yeah, there you go. Right. It's close, going a little faster. More kinetic energy. All right, Mackenzie, Alec, Big Willie, Victoria Molly, Nathan. What remains constant for a satellite in elliptical orbit? When we talk about energy, we'll talk about a principle called conservation of energy. You cannot create or destroy energy. Energy can take different forms and it can transfer from one form to another. But the total amount of energy, and we're going to quantify that in joules, yeah, does stay constant. So it's called conservation of energy. There you go. All right, so the total energy. So potential energy is like energy of position, think radial distance in this case. Kinetic energy is energy of motion. All right, but the sum of those is the same everywhere. Got SpongeBob, Alec, Big Willie, Victoria Molly, and Nathan.
So sad.
Escape speed from the surface of Earth is about.
This is just like whatever Peter was like shot in that one episode of Family Guy.
Right, where's the flash?
11.2 kilometers per second. There you go. Be about 1.4 times the orbital speed. You got 11,200 meters per second. Hey, guys, remember what escape speed means? It's how fast you have to go so you can cut off the rocket engines, but still have enough speed to escape the gravity field. SpongeBob, Big Willie, Alec, Victoria Molly, Nathan. Are we going for the win here? Is this number 20 for the win? Because a satellite is always changing direction. It loses energy as it orbits Earth. True or false?
False. You can't really lose energy, just kind of change energy. It cannot be migrated more than.
Aha! You guys remember conservation of energy? That's right. That's right. All right, to the podium. Who's on this podium? With the bronze, Alec. With the silver, Victoria Molly. And with the gold, Nathan. All right, nice job, guys.
Big
All right,
Willie would have been top dog if I didn't.
tomorrow, be ready to spin some turntable and also turn in your puzzles if you haven't turned in your puzzles yet. All right, you guys have a good day.